So then the first function that we have in our toolkit that looks like a rational function is that f at x equals 1 over x, right? 1 is a perfectly good polynomial. It's just the constant term. And we see what the behavior of that thing is. It looks like we, as x goes to 0, and when I mean this x goes to 0 from, and you see the little negative sign up on the upper right of the 0, that means from the negative side. So if I come from over here and I'm tending towards 0, my function is going to go to negative infinity. And so similarly, if I go to 0 from the right side, so I say as x goes to 0 from the positive side, like this, it goes up to infinity. And then as x goes to infinity, as it goes all the way out to the right, the function gets closer and closer to 0. And as x goes further and further out to the left, our function goes to 0 as well. So these are the 4 behaviors of this one particular function. So let's look at the other function that we have in our toolkit, which is 1 over x squared. And it looks very much like the 1 over x squared, except that left half is now above the x-axis, not below. And so using the same kind of notation that I had before, as x goes to 0 from either direction, the function goes to infinity. And as x goes to infinity, then the function goes to 0 either direction. So as x goes to negative infinity, our function goes to 0 as well. And so these two functions, I'm going to be using these in the next couple steps to characterize rational functions by either adding or subtracting or somehow relocating these things to see how they behave when we translate them. Okay, any questions before we move on? Does everybody have that?
Can I get a minute to write down the x to 0?
Yes, Kyla.
The little negative and the little plus above the 0.
Yes.
That means as it's approaching.
As it's coming from the negative side to 0 is the way to look at that. Okay. So if you see the x goes to anything, and in this case it's x goes to 0. When we put the negative sign up here, that means where it's coming from.
Okay. So
Negative numbers up to 0. This one means it's coming from positive numbers down to 0. Okay? I know it's easy to twist this thing back in your head, and when you don't see it for a while, you always have to think, well, does that mean that it's going positive or coming from the positive? And so it's really where it starts from. Okay, so the first thing that we're going to talk about are something called asymptotes. And what an asymptote is kind of a boundary, something that the function doesn't cross over. It's something that it tends towards. And so if we take our first toolkit function, this f at x equals 1 over x, and I just add 2, you can anticipate what's going to happen to this thing, right? What's going to happen to it? It's going to shift up, and it's going to shift up by 2. So then what used to be the x-axis, now we're going to call that a horizontal asymptote. Okay, so as we go from close to 0 off to infinity either direction, the value of our function is going to approach that asymptote. It's never going to cross it, and it's never going to touch it. Now if I rework that function a little bit, I'm going to add 2, so x is the common denominator, so I'm going to add 2x to the numerator. I get g at x equals 2x plus 1 over x. So this is a rational function, even though what I originally established was I just added 2 to it. I can express it in the form of a rational function, so it is a rational function. Now, what I want you to notice about this is that the degree of the numerator and the degree of the denominator, they're both 1, they're both exactly the same, and so the ratio of the coefficients, that 2 over that implied 1, is where we're going to get that horizontal asymptote. And I'll cover this a couple times, so we'll go through a few examples so it won't seem quite as esoteric as what I'm saying right now. So this is a horizontal asymptote.
G of x is the asymptote?
No, the line y equals 2 is the asymptote. The dashed line is the asymptote. So g at x has a horizontal asymptote at y equals 2. And if we go back and think about it, f at x equals 1 over x has a horizontal asymptote at y equals 0. So we would not write a dashed line over the axes, but that is the asymptote because it approaches that value, doesn't cross it, but it gets very, very close to it. Yes?
Why does 1 over x plus 2 turn into 2x plus 1 over x? Curiosity, wouldn't it be 2 over x if you changed it?
No, here I have, I'm adding 1 over x plus 2, make a common denominator, so I get 2x over x. And
Oh,
so
okay.
I get 1 plus 2x, and I've just changed the order to make the polynomial in our traditional form.
Okay.
Okay? So let's look at doing the other thing now that we know about translations. What happens to this, do you suppose? It goes right to, correct. Now, what's going to happen is that we're going to get an asymptote here, a vertical asymptote. And so what used to be the asymptote as x equals 0 is now going to be x equals 2. And so if I expand that function h at x and just write it out, I have 1 over x minus 2. And so the thing to note here is that where the denominator equals 0, you get a vertical asymptote. Okay, so we look back at the original function, the f at x equals 1 over x. And so when x equals 0, we have the vertical asymptote at x equals 0. That's hard to see. If we shift it over by 2, 1 over x minus 2, that asymptote then exists where x minus 2 equals 0 or x equals 2.
So if you shift both, you shift the whole x and y axis instead of just one bar of it.
Yes. Oh, incidentally, all of the slides now are up on Moodle. So I have the recordings that I've made of the lecture. And if I don't have a recording of the lecture, it's because either it didn't turn out or I forgot to push the record button. But all the slides will always be up there. Okay, so if you're missing a little detail on it, you can go back. And there's really not ever too many slides. It's between 6 and 10 for most days. Okay, so let's go back to this notion of the horizontal asymptotes. Make this a rule now. Okay, so I'm going to talk about a function that's a rational function. So you have a polynomial in the numerator, polynomial in the denominator. And so my rule on the horizontal asymptote, that it's going to be determined by the degree of the polynomials in the numerator and denominator. So that's the thing I'm going to look for when I'm trying to decide what's happening in terms of long-term behavior. Am I going to have a horizontal asymptote? Now the thing that's important to note here is that you're only going to have one horizontal asymptote. There's no other way that you can form an asymptote. It's just going to be horizontal. You may have one or you don't necessarily have one. For example, the linear equation, just f at x equals x, is strictly speaking part of the family of rational functions, right? X over 1 is a ratio of two polynomials. That does not have an asymptote. That's just a straight line that's a diagonal all the way through. So what I'm talking about, that if you have a horizontal asymptote, you only have one. You'll never have more than one. So then there's three cases that we have with the polynomial functions, or these rational functions where the polynomial's in the numerator and the denominator. If we have something where the numerator has the higher degree, for example, this f at x equals 3x to the 7th plus other things over 2x to the 4th minus other things, the degree of the numerator is higher than the degree of the denominator. And so the behavior that this is going to exhibit, the long run, that first term, the leading term, is going to dominate. And when x is very, very large or very, very small, this function is going to look like just 3x to the 7th over 2x to the 4th. Or if we simplify that, it's going to look like 3 over 2x cubed. Now that doesn't have an asymptote. You know what the x cubed looks like. It just starts from the lower left goes to the upper right. And so when you have a rational function with a higher degree in the numerator, no asymptote. Okay, and then you're going to expect its long-term behavior to look like just the ratio of the first two, or the first, I shouldn't say first, of the leading terms, the terms with the highest degree. Okay, so if we have the denominator now, if that degree is higher than the numerator, what happens here is very simple. As you get larger and larger, as the denominator gets bigger and bigger and bigger, it's going to be much larger than the numerator, which is, of course, smaller. And so the function is going to approach 0. And this is just like we have the f at x equals 1 over x. As x goes to bigger values, f at x goes to 0. And that's true on the negative side as well. As x goes to negative infinity, our function goes to 0. So the interesting case here, the one that we're interested in with the horizontal asymptotes, is if we have a function that has a polynomial of the same degree in both the numerator and the denominator. And so the horizontal asymptote is the ratio of the coefficients. And let me give an example here. So if we have two polynomials, one in the numerator that's 6x cubed plus other things, divided by a polynomial 2x cubed plus other things, they have the same degree, and so the horizontal asymptote is going to form at 6 divided by 2, or y equals 3. So you can just draw your dashed line right across y equals 3.
What
Yes.
happens if the denominator degree is higher? Nothing? No asymptote?
It's the first case then. No, it's the second case. There's no asymptote, and it goes to 0. Or strictly speaking, you can say that the asymptote is 0 if you want, but the long-term behavior just says that the function's going to go to 0.
Okay.
So those are the three possible cases. Either a higher degree in the numerator, which means no asymptote, a lower degree in the numerator, which means that either you can look at it as the asymptote being 0, or the function will go to 0 in the long run, or when they're equal, it's going to be the ratio of the coefficients. All right, let's go on to vertical asymptotes. You can pick it up at the off the charts that are posted.
So the only one that creates a horizontal asymptote is the last case.
It's the last case where you have the same degree on the numerator and the denominator. Now I'm going to talk about vertical asymptotes, and we'll go through some examples, and it'll become a little bit more visually familiar then. Okay, I know these are a lot of rules to digest and everything, so I'm going to talk about vertical asymptotes now. Now, vertical asymptotes are easy to pick out because it's where the denominator polynomial equals 0. So the way you figure out where your vertical asymptotes go is just what are the roots of the polynomial in the denominator. So if you have this function here where you have 3x squared plus x plus 1, and I'll have it factored, okay? We're not going to belabor this by showing a fully expanded polynomial, but you're going to factor it, and then you're going to find that you have roots at of that denominator at x equals 1, negative 2, and 3. That's where your vertical asymptotes go.
Can't you not divide by 0 though?
That's exactly why you get an asymptote, because then that's kind of a hole in the domain. You know, your vertical asymptotes are the exclusions to your domain. Those are numbers that you can't have. Okay, so let's look at go back to that f at x equals 1 over x. The short-term behavior, remember, as you came from the positive side, it went up to infinity, and when it came from the negative side, it goes down to negative infinity. And so the direction of how the numbers go is an alternate fashion. It's on one side it goes to infinity, the other side it goes to negative infinity. And if we put a negative in front of it, then it'll be just the opposite. So what this means is that when you have an odd power in the denominator, that means the short-run behavior is going to go to the opposite infinities, if you want to look at it that way. Remember when we had 1 over x squared, the short-term behavior of that means that as it goes to a value, it'll go to infinity or negative infinity on either side. Okay, so it looks like, you know, think of 1 over x squared as looking like that volcano. All right, so when you have an odd exponent, it does this, it alternates. When it has an even exponent, the infinities are on the same side. So if, whether it's positive or negative, these things, the direction of infinity, in this case, is the opposite. It's the negative infinity on the left side, positive infinity on the right. On this one, because it goes to positive infinity on the right, it also goes to positive infinity on the left. And that's going to be true in general. So anytime you have an even power, then it's going to be the infinity behavior as you get close to your asymptote is going to be the same.
So I guess I'm getting a little bit confused on like what would be short-term versus long-term behavior then.
Mm-hmm.
So you're saying that the short-term behavior here is that, like say on that first one, as the denominator goes up, our y goes way up to infinity. That's short-term behavior.
Yeah, the short and long-term behavior refers to what the value of x is. So when x is very, very large or very, very small, that's the long-run behavior. The short-run behavior is when x is close to your asymptotes, or where x is your roots, or things that we tend to graph. You know, when x gets very, very large or very, very small, we just stop and we put an arrow and say it goes on like this. But with short-term behavior, these are the things that we note where we have local values of x. And so by short-term behavior, I'm talking about x being close to 0 for 1 over x and 1 over x squared. The long-run behavior is when x goes to infinity or negative infinity. Now, the function can go to 0 or infinity or whatever for the local behavior. Yes?
So a graph can have only one horizontal asymptote but multiple vertical asymptotes?
Exactly.
What does that look like?
Well, we're going to have some examples here where we're going to graph these. Okay, now with these polynomial functions, we're going to have intercepts as well. And so the y-intercept is just exactly the same as it's always been. You evaluate f at 0. So when x is 0, what does f at 0 equal? The x-intercepts are going to be where your function equals 0. So you can't have 0 in your denominator. That's where your asymptotes are going to be. But in the numerator is where you're going to have your x-intercepts. So long as q of x is not 0, p of x says where your x-intercepts are. Now we're also going to have something that we haven't seen too much of before, these holes in the function, what I call. And I call them a hole because we're going to actually draw a little hole. These happen when we have a domain restriction, and the domain restrictions in these polynomial or in these rational functions will come from simplifying functions. Like let's say we have this function x plus 1 divided by x plus 1 over x minus 1. Okay, so we can simplify that by canceling the x plus 1 factor in the numerator and the denominator. So we know that x can't equal negative 1 even though we've simplified it, and this would make perfect sense, this 1 over x minus 1 at minus 1, right? That'd be 1 over minus 2. But since our original function had those factors in there, it's a domain restriction, and so we have to exclude that from the graph. So if we know what the graph of this will be. That's going to look like 1 over x, but it's going to be shifted to the right 1 unit, right? That asymptote is going to be at x equals 1. And so it's going to look like this. But remember, at negative 1, I can't have that because I have x plus 1 over x plus 1. That's 0 over 0. That doesn't have a numerical meaning. And so we erase, we make a gap in the function, and we put a hole in it. And so what that means is that that's not part of the function. There is no value for x equals -1. And so you have to look at the original function to look for these holes. So we have two things going on. If you look at the denominator, you have x plus 1 and x minus 1. If you just looked at that superficially without trying to simplify it first, you might say you have two asymptotes, one at -1 and one at 1. Well, that's not true because you have the x plus 1 in the numerator, which cancels out the x plus 1 in the denominator. And so it's a domain restriction, not, it's a hole, not an asymptote. Yes?
So then are the domain restrictions, like for all of these equations, always going to be a would-be asymptote that's not?
A domain restriction will be one of two things. It'll either be an asymptote if it doesn't simplify out, or if it simplifies out, it'll be a hole. Because think about the graph of x plus 1 over x plus 1. For all other values other than x minus 1, it's just going to be a straight line, right? It's just going to be 1. So if you were just to graph that straight line, you'd have to draw a hole at x minus 1 because it can't be that. It's a domain restriction there. Okay, so I gave you a long laundry list of rules. And so let's put them all together and make a couple graphs, all right? And this is going to take some practice. And so tomorrow at tutorial is going to be a pretty important tutorial because you're going to have a lot of practice on these kinds of things. And I would imagine we're going to spend a fair amount of time on Friday talking about these as well. And so don't worry so much if you can't get it right away. With practice, you will. Okay, so what I want to do is I want to sketch this function. I want to sketch 2 times x plus 1 times x minus 2 over x minus 1 and x plus 2. So I look at that and I think, okay, is there any simplification I can make in this? And the answer is no. There's no common factor between the numerator and the denominator. So I'm not going to have any of these holes that I just talked about. But let's go through and look at each of the things, each of the features that we were talking about earlier about vertical and horizontal asymptotes and roots and intercepts. Let's see what we know about this. So the numerator and the denominator degree, so if we multiply it out, we're going to get an x squared on the top and the bottom, right? So we have a horizontal asymptote at the coefficient. And so you can imagine when you're expanding the top, you don't have to do the whole polynomial. You just look at the highest degree term, which is just x. So you have x times x, then you have a constant 2 that's in front of that. So you're going to have a 2x squared plus other things over x squared plus other things. And so your horizontal asymptote is going to be y equals 2. Okay, so let's look at vertical asymptotes now. Vertical asymptotes, remember, are the roots of the denominator, and so we have x equals 1 and x equals -2. And so we have a y-intercept. If we just plug in a 0, we get 2 times 1 times -2 over -1 and 2, so all those x's become 0, and that's what we get. So we have a y-intercept at 2. So there's a point that we have. And then the x-intercepts is where the numerator is 0. So we know that that's going to be x equals -1 and x equals 2. So now we have a whole bunch of things that we can put on a plot, and then we can kind of figure out what this whole graph looks like. Okay, so I'm going to draw some axes. Draw my horizontal and vertical asymptotes. And then the next thing I'm going to do is I'm going to put in the points that I know. So I know my y-intercept and I know my x-intercepts. Okay, everybody follow me to this point? You feel like if you can identify those asymptotes, you can draw them, and then the 3 values that we know, the 2 x-intercepts and the y-intercept, we can plot.
How do we go y-intercept at 2 if we have the horizontal asymptote 2?
Well, because the horizontal asymptote, that's a really good question. The horizontal asymptote determines long-term behavior, not short-term. Okay? So what we're going to find is that with these vertical asymptotes, we have regions. And so the regions are going to behave differently. And so the regions on the extremes, the extreme left and the extreme right, that's where your asymptote plays in. It doesn't really, it may play into this middle section, but it looks like it's not going to. Okay? Very good question, though. Okay, so we know that as x goes to positive 1, or as x goes to 1 from the positive side, so we're coming down this way, we're going to end up at negative infinity. Now look at the notation that I made there. What I did was I put the coefficient there, because sometimes the coefficient can be negative, and then I put parentheses where those terms are, and all I did there was I put the sign of what that term is going to be. So in the position where I have x plus 1, okay, if I'm going to 1, that's always going to be positive, right? Because I'm coming from either very large positive numbers going down to close to but not exactly 1. So that's going to be positive. So then the second term is that x minus 2 in the numerator. That is going to tend to be negative, right? Because if I'm getting close to 1, that's going to be close to 1 minus 2, which is negative. So I'm going to put a negative there. And then on the denominator, okay, what I'm going to have is x minus 1 is always going to be positive, and x plus 2 is always going to be positive as well. So as I go to, from the right close to my asymptote, I'm going to go down to negative infinity. Now you'll notice that when x equals 2, remember we're going to go through that point, on the right side, that function now is positive, and that's what we expect, because if we maybe change this as x goes to infinity, those will all be positives, and so we know it's going to be positive, but it's not going to go to positive infinity. It's going to go to our asymptote, which is 2. So it's going to climb up there. So there's the first part of our curve. Now, what happens on the other side? So as we go to 1 from the left side, so we're coming this way, we do the same thing. We say, okay, the x plus 1 is going to be positive. The x minus 2 is going to be negative, and then on the denominator, since x is going to be slightly less than 1, x minus 1 is going to be negative, and x plus 2 is going to be positive, so this is going to go to infinity. And so we're going to start way up at infinity, we're going to come down, go through the y-axis, we're going to go through the x-axis at our intercept, and then it's going to go to infinity, or negative infinity, as we approach the other asymptote. So as x goes to negative 2, from the negative side now, we see that this is going to go up to infinity. And so we can make a pretty reasonable conclusion that we have something that looks of that shape. So let's think about some of the other things that I was talking about. So when we have the 1 over x, not 1 over x squared, the short-term behavior infinities, whether it goes to positive infinity or negative infinity, alternates. And we see that. It alternates here. It goes from negative infinity, positive infinity, negative infinity, positive infinity. If one of those terms had been like x minus 1 squared or something like that, we would expect that the infinities would be on the same side, either both positive or both negative. But that's not the case here. And you're thinking at this point, what did I buy into when I took this class, right? Okay. Let's try another one. Okay. So we have f at x equals x plus 3 over x plus 1 squared and times x minus 2. So let's look at the long-term behavior. As x goes to infinity, f is going to go to 0, and as x goes to negative infinity, f is also going to go to 0. Why does it go to 0? The degree, right. The denominator degree is higher than the numerator degree. So the long-term behavior says it's going to go to 0. Okay, so we have some vertical asymptotes. One of them is going to be -1 and the other one's going to be 2. Because if x is either -1 or 2, we're going to have division by 0. So we have to put an asymptote there saying we're not going to ever be there. The y-intercept, we plug in a 0, and so we get 3 over 1 squared times -2, and so our y-intercept is going to be -3/2. We only have one x-intercept because there's only one way that this thing can be 0, and that's when x plus 3 equals 0, so x equals -3. And so that's about all we can get from looking at that function. So we start graphing. We put our two vertical asymptotes. We put the, I'm running ahead of myself here. Let me back up. Okay, so we put the vertical asymptotes there at 2 and at -1, and we have two intercepts. We have the y-intercept at -3/2, which is 1.5, so I put my orange dot there. And then my other one is going to be at x equals -3. Now I didn't label these with numbers just to remove the clutter, but somewhere if you're making these graphs on a larger piece of paper, you should be putting what your scale is. And so you don't have to populate it with everything, 1, 2, 3, 4, 5, but put enough numbers on there so the reader will know, is 1 mark 1, or is it 5, or is it 10, or something of that sort. So I would, encourage you to get in the habit of labeling the x and y axis, even though here I don't think the space warrants it. Okay, so then let's look at the behavior as we approach the asymptotes. So on this first one, as we go to 2 from the positive side, so we're coming down here, all right, we know that we're going to be close to 0 where with the long-term behavior off to the left. Which way is it going to go? Up to infinity or down to infinity? All right, so the top one, as we're approaching 2, is positive. The x plus 1 squared is always positive because it's squared. And then we have x minus 2, and since we're slightly greater than 2, we're going to always be positive there, so it's going to go up to infinity. Now if we look at it from the other direction, if we come back this direction, from the right, and we're heading towards the x equals 2 asymptote, we'll populate that, and so what we get then is the top is still going to be positive, the numerator, the denominator x plus 1 squared is going to be positive, but that x minus 2, since x is just slightly less than 2 as we're approaching 2, that's going to be negative, so we're going to go to the negative infinity side.
And these are all short-term behavior.
These are all short-term because I'm looking what happens as I get close to my asymptotes. My long-term behavior I already established. It's going to go to 0.
And then one last question, the y-intercept, you're taking, I guess, just that little constant term, 3 over the -2 for whatever reason?
I'm putting in f at 0 is my y-intercept. Okay, so 0 plus 3 over
right.
0 plus 1 squared.
Sorry.
Okay, so let's look at the behavior as my function goes off to the other asymptote, and I'll put both of them up here and then make some comments on it. Okay, so as we go from the right side towards the x equals -1 asymptote, what happens? We put our values in there. The numerator is going to be -1 plus 3, which is still positive. The denominator, the x plus 1 squared, is always positive. So what happens is x minus 2, that thing's going to be negative, right? Because as we go to -1, that whole value is going to approach -3. And so we're going to go to negative infinity as we go close to this asymptote from this direction. So we're going to expect it to go down like this. Now if we come from the other direction like this, we're going to evaluate the same thing. We get a positive in the numerator and we get a positive and a negative in the denominator. But we also have another clue. Since that x plus 1 squared, the x plus 1 is the thing that kind of caused this asymptote. And since that's squared, here you know your infinities are paired. They're either both going to be positive or they're both going to be negative. And sure enough, when we plot this thing, this is what it looks like. All right, so we have the first line is that first curve. And notice that I'm keeping that above the x-axis. There was no intercept there, so I have no reason to cross the x-axis, and I'm coming from infinity and going off to 0, so I'd expect to stay to the right of the asymptote and above the x-axis. Now I'm coming from infinity. I know I'm going through x equals, or I'm going through y equals -3/2, and I'm going to infinity again, so I have this thing that turns around. Now exactly what the peak of that thing is, we haven't answered that question. We're going to get to that in a couple weeks about where does that occur. But for now I'm just going to make a sketch and say this thing turns around somewhere. And then my short-term behavior on the left side of that asymptote goes down to infinity. But here I have an intercept, right, an x-intercept. So I'm going to go through the x-axis, and then I'm going to level off towards 0. So exactly how high do I go before I start leveling off to 0? That's not a question we can answer with just what we have. So I'm just making it turn that direction. Okay? So a couple more comments on this. Okay, so there's that effect. You know, the x plus 1 squared means that I have both of my infinities going to the same direction on either side of the asymptote. And then I'm going from negative to positive if I look at this term. And so I'm going to be just above the x-axis as we go off to infinity. So I put this in a program, and I drew a graph, and lo and behold, this is what I get. And so I'm pretty right in my graph. Now, it doesn't go out to -3, so you can't actually see it cross the x-axis there, but it does, and it levels out. This line right here is just an artifact from the graphing program. It just goes all the way up as far as it can go, and then it sees the next value is really, really far down, so it draws a straight line. So this is actually a representation of the asymptote, not of the function itself. And you can see the y-intercept at y equals -3/2, and that we do have a peak to the right, but like I said, we don't really have any basis right now for deciding which side of the y-axis that happens on, so we're content with this thing just turning around. Now we got the other side of the coin, is we're going to make equations from graphs. And so I'm going to draw a graph here, and we'll see what we can do in terms of getting its equation. So I'm going to label everything up. And so I have this graph. I have two asymptotes vertical. They're x equals 1 and x equals -1. I have a y-intercept at 0 and 2, and I have an x-intercept at 2 and 0. Okay, so let's look at this. The long-term behavior, our function goes to 0, so we're going to then conclude that the denominator degree has to be higher than the numerator degree. Since we have vertical asymptotes, we know that the function is, well, we know what that means to the function. And let me let this write out, and then I'll explain where I get these things. We'll stop there. Okay, so let's look at, before I write that second equation here. Let's look at this. Okay, so I know that the numerator is going to be x minus 2, because that's what's going to put a 0, that's what's going to give me my y-intercept. My denominator is going to look like x plus 1 times x minus 1, because I have two vertical asymptotes at 1 and -1. And then I always have this coefficient a, and the coefficient a is what's going to make this whole thing work when I plug in real numbers. Okay, so what value do I actually have here? The only value that I have is f at 0. And so when I know that that thing is going to equal 2, f at 0 is 2, so when I plug in a 0 with my x, I find that a times negative 2 over 1 minus negative 1 is going to be 2a, and so a equals 1, and so my function then is going to be x minus 2 over x plus 1 times x minus 1. Okay, so the numerator determines that y-intercept, the denominator determined the vertical asymptotes. I stuck in a coefficient a to reconcile the function to make sure that it works the way I expected. And the x minus 2 in the numerator comes from the fact that I do have an x-intercept there. Okay, there's one last one. Yeah, we have about 2 minutes left in the class, but I'll do that. Okay. Okay, so let's look at the next one, and the next one here I think will probably take some studying on your own because it does go kind of fast. If I have a function that looks like this, so I have a big mess here where I have the x and y intercept at 0, 0, and then I have a horizontal asymptote at negative 2, and I have vertical asymptotes at negative 2 and 3. I know what my numerator looks like for my vertical asymptotes. I know my numerator, or I know what my denominator looks like from the asymptotes. The numerator has to be third degree to get my horizontal asymptote. I have one intercept. And so what I get out of this thing here is the form of it looks like this f at x equals negative 2 times some factor over those two factors that give me my asymptotes. I get x cubed there because that's my only intercept. So when x equals 0, that's my intercept. And I know it's cubed because that thing flattens out. Remember the short-term behavior of 1 over x cubed. And I have to match that degree with the degree in the denominator, which is x plus 2 squared, which gives me an x squared. And then I have an x from the x minus 3. So everything that you know about them, about these functions, fits in this form.